The transition from a coherent fighting ship to a sinking wreck occurred in 20 seconds. This is not an estimate, it is the recorded duration of the structural failure that destroyed the light cruiser United States ship Juno. In naval engineering terms, this is an irreversible threshold. A warship is designed to absorb damage, to flood partially, and to remain stable enough for damage control. Juno was denied that opportunity. When the torpedo from the Japanese submarine I-26 struck her port side, it did not merely breach the hull. It detonated the forward magazines. The resulting overpressure event did not just sink the ship. It disintegrated the midship section entirely, severing the bow from the stern and terminating the vessel's structural integrity instantly. This documentary is a forensic examination of what remains. The objective is not recovery. The site is a designated war grave, legally protected and ethically restricted. 687 men were lost, including the 5 Sullivan brothers. Consequently, the salvage engineering logic here is inverted. We are not calculating lift weights or cutting plans. We are analyzing the physics of the wreck to document the site without disturbing the sediment. The constraint is absolute. We look, we map, and we leave. To understand the debris field, we must first understand the mechanics of the loss. Juno was an Atlanta-class cruiser designed for speed and anti-aircraft volume rather than heavy armor. On November 13, 1942, she was already damaged, limping away from the battle area, down by the bow with compromised systems. The second torpedo struck the same general area as the first. This compound damage created a failure cascade. The magazine detonation generated a shockwave that exceeded the yield strength of the keel and shell plating. Witnesses on adjacent ships reported a massive cloud of smoke and debris where the cruiser had been moments before. The violence of this event has a specific hydrodynamic consequence. Usually, when a ship sinks intact, it must battle the increasing hydrostatic pressure as it descends. If the hull is sealed, it risks implosion. Juno faced a different physics profile. Because she was torn open at the surface, the water pressure equalized instantly inside the compartments. She did not implode on the way down because she was already destroyed. The heavy sections, the bow, and the stern began a free fall through the water column, independent of each other. This creates a chaotic entry into the abyss. Heavy machinery, turrets, and bulkheads were liberated from the hull structure and tumbled separately. In a standard sinking, we expect to find a linear debris trail leading to a main hull. Here, the violence of the magazine explosion suggests a scattering effect, throwing debris over a wide radius. However, the survey data reveals a contradiction. Despite the explosive force pushing the ship apart at the surface, the largest sections of the wreck did not scatter as expected. The depth of the water column provided time for hydrodynamics to act on the falling steel. As the sections fell, they planed, rotated, and drifted based on their center of gravity and drag coefficients. This ballistic trajectory through 13,000 feet of water determined the final resting place. It is a long fall. It takes time for a piece of steel to reach the bottom, and during that time, currents and drag alter the impact point. The result is a debris field that defies simple geometric logic. We have a ship that blew apart, yet the survey reveals a concentration of mass that requires explanation. The failure was instant, but the preservation is timeless. The darkness and cold of the deep ocean have arrested the decay, locking the ship in the state she entered the water. We are left with a forensic puzzle. How does a ship that disintegrated at the surface land in such a specific, technically impossible configuration at the bottom? 13,800 feet of water creates an effective quarantine. For the wreck of USS Juno, this extreme depth is a critical engineering constraint, acting as both a preservation agent and a barrier to immediate investigation. Unlike shallow water wrecks exposed to wave action, currents, and marine life, the abyssal plain offers a near-static environment. Here, steel corrodes at a significantly slower rate, and the lack of oxygen inhibits biological decomposition. This is why the Juno's structure, despite its violent end, exhibits a degree of preservation that surprises many. The survey by RV Petrel confirmed this phenomenon. The wreck lies at 4,200 meters. This depth alone meant that any conventional salvage operation would be extraordinarily complex and expensive, requiring specialized, remotely operated vehicles and advanced subsea engineering. It also meant that Juno would remain undisturbed for decades, a silent testament to the ferocity of the battle she met her end in. The initial damage analysis, supported by witness accounts and later forensic surveys, points to a single, catastrophic event, a magazine detonation. The second torpedo impact, striking near the forward magazines, initiated a chain reaction. This was not a slow flooding or a gradual structural collapse. This was an instantaneous release of immense energy. Forensic evidence from the wreck site, specifically the port side hull plating, supports this. Instead of bending or tearing, the plating appears to have been peeled outward, much like a can of food opened with a knife. This is direct physical evidence of extreme internal overpressure, a signature of high explosive detonation. This violent dismemberment also liberated heavy components from the hull structure. Among these is a 5-inch gun mount. This particular mount, identified from sonar data and later ROV imagery, exhibits damage consistent with being ejected from the ship during the explosion. It landed in the debris field some distance from the main hull. What makes this finding notable, beyond its separation, is its physical state. The mount itself has been blown in half. This catastrophic failure of the mount provides a unique, almost cutaway view of its internal mechanism. It offers an archaeological glimpse into the components that operated just moments before the ship's destruction. We can see how the mount was constructed and how the force of the explosion fractured it. Furthermore, this separation and damage provide a crucial data point for understanding the forces at play. The sheer power required to rip a heavy gun mount from its mountings and then fracture the mount itself underscores the magnitude of the magazine detonation. It is not just the main hull that tells the story. These liberated components are also critical pieces of evidence. They confirm the explosive nature of the sinking and provide tangible examples of the forces involved. The abyssal environment, while preserving steel, introduces its own set of challenges. The extreme pressure at 13,800 feet is immense, but the hull was already compromised. It did not need to withstand implosion. It needed to survive the fall. However, the true story of the Juno's final moments is told not just by the main hull sections, but by the way these heavy, liberated components settled on the seabed. The manner in which these pieces landed and their positions relative to the main wreck provide vital clues about the dynamics of the sinking. The violence of the break suggests a wide scattering of debris. Yet, the primary wreckage exhibits a surprising lack of dispersal in its largest sections. This apparent contradiction is a key question driving the continued analysis of the sonar data. While the hull plating and gun mounts reveal the how of the sinking, the spatial distribution of the wreckage will reveal the where and the why of its final resting position. The deep, hostile environment has preserved the evidence, but it has also hidden the complete picture. Side-scan sonar does not see steel, it sees acoustic shadows. When a survey team hunts for a target at 13,000 feet, they are not looking for a photograph. They are looking for a disruption in the noise. The seabed is a soft, sound-absorbing layer of sediment. A man-made object, by contrast, is hard and reflective. It returns a sharp acoustic ping, leaving a dark shadow behind it on the display. This contrast is the primary evidence gate for locating a deep water wreck. For the research vessel Petrel, the initial search grid presented a distinct anomaly. The acoustic return did not show a single linear debris trail consistent with a sliding sinking. Instead, the map revealed major wreckage concentrations separated by roughly a kilometer, consistent with the bow and stern lying close together while the midships section lies farther away. This separation distance is the first clue to the ballistics of the sinking. It confirms that the midships section, the area obliterated by the magazine detonation, disintegrated sufficiently to separate the bow and the stern into independent falling masses. To resolve the resolution limit of sonar, the team deployed a remotely operated vehicle. This transition from acoustic mapping to optical survey is the moment the geometry of the wreck becomes clear. The sonar provided the location, but the camera provided the orientation. What the lights revealed at the primary target site was a configuration that defies standard probability. Public reporting from the discovery describes the stern lying next to the bow. The two major sections are extremely close, while the midships wreckage lies farther away. In the chaotic tumble through the water column, the bow section likely impacted the seabed first, driving deep into the sediment. The stern section, following a similar hydrodynamic wake, or perhaps loosely tethered by wreckage that eventually failed, impacted moments later. it landed squarely on the forward structure, crushing the bow beneath its weight. This stacking effect creates a complex visual environment for identification. The bow is largely obscured, flattened under the mass of the aft hull. However, the stern stands proud of the mud, upright and recognizable. It is here that the survey team found the ultimate verification of identity. On the very end of the fantail, despite 76 years of immersion, the raised steel letters of the ship's name remain legible. The name Juno is clearly visible, welded to the steel. This survival of the nameplate is a low probability event. Usually the violence of the impact or the subsequent corrosion obscures such fine detail. In this case, the positioning of the stern, held high off the mud by the crushed bow beneath it, kept the nameplate clear of the sediment line. This allows for a positive identification without the need for physical interaction. We do not need to recover a bell or a builder's plaque to know what we have found. The ship identifies herself. The debris field surrounding the central stack tells the rest of the story. While the bow and stern are locked together, the midships section is 2,000 feet away, a field of shredded plating and machinery. This distribution confirms the total structural failure at the surface. The ship did not break and float, she broke and fell. The lighter, more aerodynamic bow and stern sections planed away from the heavy, non-aerodynamic debris of the center section. The 2,000-foot gap is the physical measurement of that hydrodynamic separation. This mapping effort shifts the understanding of the site from a mystery to a defined grid. We know where the main hull lies, we know the bow is inaccessible, buried by the stern, we know the midships is scattered. The survey objective now shifts from localization to detailed forensic inspection. With the heavy geometry mapped, the focus turns to the smaller details, the evidence that survives on the steel itself. Steel rots in salt water, but brass and glass possess a different chemical timeline. When a warship sinks, it becomes a battery. The seawater acts as an electrolyte, facilitating the flow of electrons between dissimilar metals. In most shallow water wrecks, this galvanic corrosion accelerates the decay, consuming the iron to protect the noble metals like bronze or brass. However, at 13,800 feet, the chemistry changes. The extreme pressure and low temperature reduce the dissolved oxygen levels, slowing the oxidation process significantly. This creates an environment where delicate details, usually lost within decades, can survive for the better part of a century. This preservation anomaly is evident on the 5-inch gun mounts of USS Juno. The survey team located a specific mount in the debris field that offers a rare insight into the ship's pre-combat status. On the side of the steel housing, a painted letter E is still clearly visible. This is the Battle Efficiency Award, a standard United States Navy decoration denoting a crew that has exceeded performance standards in gunnery exercises. The survival of this paint is technically significant. Paint is an organic polymer. In shallow water, microorganisms and ultraviolet light degrade the binder, causing the pigment to flake away. In the deep ocean, those degradation vectors are absent. The E remains distinct against the rusted steel, not because of luck, but because the biological consumption rate at this depth is near zero. It freezes the ship in time, preserving a mark of pride applied by the crew in 1942. Moving from the gun mount to the fire control systems, we see another example of material resilience. One of the Mark 37 gun directors was located with its access hatches blown open. This director was the brain of the ship's anti-aircraft defense, a complex electromechanical computer designed to track incoming aircraft. The open hatches allow the remotely operated vehicle to inspect the interior. Inside, the optical glass of the rangefinders and sighting telescopes remains intact. Glass is chemically inert in seawater. While the steel casing around it corrodes, the lenses remain clear. This creates a jarring visual contrast. The heavy structural steel is pitting and thinning, slowly dissolving into the ocean, while the fragile glass components look exactly as they did on the day of the sinking. This differential preservation allows forensic historians to verify the specific modification standards of the equipment. We can identify this as an early war variant of the Mark 37, confirming the ship's configuration matches the 1942 fitting out records. The presence of these intact sensors also confirms the mechanical violence of the loss. For the director to be found in the debris field, it had to be torn from the superstructure. The bolts shearing or the deck plating failing requires immense force. Yet the director itself is not crushed. It was liberated from the ship by the shockwave and then fell through the water column largely intact. It did not suffer the crushing impact of the main hull. This evidence presents a duality. The heavy structural elements, the hull plating, the keel, the bulkheads, are shredded and twisted by the explosion. But the smaller, more fragile components, the glass sights, the painted letters, the brass plaques, survive with high fidelity. The deep ocean filters the evidence. It destroys the macrostructure through corrosion over centuries, but it preserves the micro detail. We can read the name of the ship and the awards of the crew, even as the ship itself slowly dissolves. The main hull tells us how she died, tearing apart under internal pressure. But it is the debris field that tells us how violent the separation really was. As we move away from the heavy hull sections, we find objects that should not be there. Heavy machinery that was thrown clear of the wreck, landing in isolation on the seabed. Heavy machinery does not glide underwater, it falls ballistically. When a component as massive as a ship's rudder or a torpedo launcher is severed from the hull, it becomes a free-falling object governed by its center of gravity and drag profile. It does not drift like sediment, it plummets. The final resting position of these heavy items provides a vector analysis of the ship's disintegration. By mapping where they landed relative to the main hull, we can reverse engineer the forces that tore them loose. The survey of the debris field yielded a significant discovery regarding the ship's offensive capabilities at the moment of loss. The quadruple torpedo tubes, mounted amidships, were located among the wreckage. Inspection reveals that the tubes remain loaded. The warheads of the torpedoes are visible inside the launchers. This is a definitive forensic status marker. It confirms that despite the intensity of the night action, Juno had not expended her full salvo. She died with her weapons ready. The presence of the torpedoes also adds a hazard constraint to the site. These are live ordnance containing high explosives that have been unstable for 76 years. They represent a dormant chemical threat that reinforcing the rule of non-intervention. However, the most hydrodynamically complex object in the debris field is the rudder. In the majority of shipwreck scenarios, the rudder remains attached to the stern, or it is buried deep in the mud due to the stern impacting first. On this site, the survey team found the rudder completely detached. It lies alone in the sediment, inverted. The physics required to produce this result are extreme. A rudder is secured by a massive steel stock and supported by the hull structure. For it to be found separated and upside down, one of two things occurred. Either the initial magazine detonation created a shockwave powerful enough to snap the rudder stock instantly, or the hydrodynamic forces acting on the falling stern section tore the rudder loose during the descent. The fact that it is inverted suggests a tumble. As the rudder fell through 13,000 feet of water, it rotated. Its center of gravity, likely the heavy steel stock, would orient towards the bottom. For it to land inverted means it likely struck the bottom and toppled, or its center of gravity was altered by attached wreckage. This separation confirms that the stern section did not just fall, it suffered a catastrophic structural failure of its own, likely shedding the rudder before it impacted the bow. This brings us to the conclusion of the forensic survey. The objective was to identify the wreck and document the condition of the site. The evidence chain is now complete. We have the positive identification from the stern nameplate. We have the causal evidence of the peeled hull plating confirming the magazine detonation. We have the ballistic evidence of the scattered gun mounts and the inverted rudder confirming the violence of the breakup. The mission of the research vessel Petrel was not to disturb the site, but to lock these facts into the historical record. The survey has achieved a Path S outcome, success. The ambiguity regarding the exact condition of the wreck has been resolved. We know where she lies, we know how she rests, and we know that the violence of 1942 has been preserved in the geometry of the steel. The physics of the loss are no longer theoretical. They are mapped. With the engineering questions answered, the final phase of the documentation is not about steel or hydrodynamics. It is about the legal and ethical boundary that surrounds this coordinates. The survey data is locked, but the site itself remains a protected space, defined not by what can be recovered, but by who remains aboard. The definition of a war grave is not sentimental. It is a legal boundary against intervention. Under the Sunken Military Craft Act, the wreck of USS Juno remains the sovereign property of the United States Navy. It does not belong to the finders. It does not belong to the ocean. It is a sovereign asset that has not been abandoned, merely displaced to a depth of 4,200 meters. This legal status creates a hard operational constraint for any survey team. The license to look is granted, but the license to touch is permanently denied. This restriction is enforced because the site is a final resting place for 687 men. The loss of Juno was near total. When the magazines detonated, the survival rate was statistically negligible. Only 10 men eventually survived the sinking and the subsequent ordeal in the water. This number, 10 survivors out of a crew of nearly 700, defines the magnitude of the loss. Among those lost were the 5 Sullivan brothers, a singular loss of life for one family that directly influenced future naval assignment policies. For the survey team, this human cost translates into a strict non-disturbance protocol. The remotely operated vehicle must fly with precise buoyancy control to avoid thruster wash disturbing the sediment. We map the site, but we do not clean the hull. We identify the weapons, but we do not safe them. The wreck is treated as a crime scene that has been closed, sealed, and archived. The final visual inspection of the wreckage reinforces this sense of finality. One of the last details documented by the expedition was a crane boom collapsed across the portside torpedo tubes. In life, this crane was used to load aircraft and boats. Now it lies crushed against the weapon systems, a tangle of steel that marks the collapse of the ship's functional architecture. It is a mechanical snapshot of the moment the structure failed. The crane did not rust into that position, it was smashed there by the hydrodynamics of the sinking. The outcome of the Petrel expedition is classified as a Path S success. The primary objectives were achieved. The ship was positively identified through the stern nameplate. The condition of the hull was mapped, confirming the magazine detonation theory. The debris field was characterized. Crucially, this was accomplished without recovering a single artifact. The data is the recovery. The high-resolution video and sonar maps preserve the ship in digital form, allowing engineers and historians to study the wreck without violating its physical integrity. There is a distinct discipline in knowing when to stop. Technology now exists to cut into the hull, to lift the guns, or to recover personal effects. But engineering capability does not imply operational permission. The decision to leave Juno exactly as she lies is a deliberate choice. It acknowledges that the physical evidence, the inverted rudder, the peeled plating, the open gun directors, is sufficient. We do not need to bring a piece of steel to the surface to understand the cost of the event. The wreck of USS Juno will likely never be visited by human eyes. It requires robotic intermediaries and millions of dollars in operational funding to reach. The darkness at 13,000 feet is absolute. The corrosion will continue, driven by the slow, inevitable chemistry of the deep ocean. The steel will thin, the decks will collapse, and eventually the nameplate will fall into the mud. But the survey record is permanent. We have locked the coordinates and the condition into the ledger. The investigation is complete.